In this video, we go over how to create a data display from given quantitative data. This actually branches off of the last video that I created about creating group frequency distributions. We review that quite a bit here with slightly more difficult data, just to review and also show you a different aspect of how data can be presented to you. So we take a look at this given data set, and it asks us to create a frequency distribution, a group frequency distribution of the weights of 25 envelopes measured in grams. And we notice that all these data values go to the tenths place. If even just one of the values go to the tenths place, it basically changes everything that we do in terms of the group frequency distribution and the class width. So it's asking us to find the class width with 5 different classes. We already know how to construct the class limits, the class boundaries, the frequency, and the relative frequency from the previous video. The new ones are the midpoint, cumulative frequency, and the cumulative relative frequency, which we'll touch on each one of them. So first, let's start with the class width. We put all of these values in our graphing calculator, and then we go to Stat, Sort A, and we'll sort L1. This helps us to identify the min and the max that we can easily calculate the range. If you need more details on that, refer to the previous video. So the range is equal to the maximum minus the minimum. The minimum of this data set is 0.1, and the maximum is 4.7. So I subtract the two, and I get a range of 4.6. Now, since they wanted us to create a class width with 5 classes, our n is equal to 5. Remember that we always have to round up. Now, in this particular case, all of our values go to the tenths place, or even if just one of them went to the tenths place, we now can't really round up to 1 automatically, or round up to the nearest whole number automatically. Since each of our data values go to the tenths place, or like I said, even if just one of them goes to the tenths place, now our class width we will round up in the tenths place, not the ones place. So in this particular example, we take 4.6 and divide it by 5, and we get 0.92. Now, of course, we're taking a look at this 0.9 value. And because it's 0.9, we have to round up to the next tenths place, which would actually be 1. All right? So keep this in mind. If there is a class width, let's just say an example is that for this given data set, let's say, what if we had a class width calculation and R over N comes out to be 0.845. Again, since all of these go to the tenths place, I look at the tenths place, and no matter what that value is, I'm going to round up. So our class width would actually be 0.9. Now, what if our class width came out to something like 0.301? Again, we're looking here, and no matter what, we are rounding up to the next tenths place. All right? Even if, be careful, if you get something that's perfect and looks like this, 0.3, well, remember, we still have to round this value up, so it would still be 0.4. I just wanted to kind of give you a couple of additional examples to make the point very clear. So, again, since the values go to the tenths place, and that's the most specific digit, that means our class width has to represent that, and that's the digit that we have to round up. So we start with our class limits with a maximum of 0.1, and then we add 1 to each one of the lower limits to get to the next class lower limit. Then, in order to get to the upper limit, this is an important part to pay attention to, instead of subtracting 1, we are actually going to subtract 0.1. And again, that's because that's the most specific digit in our data set. So now we subtract 0.1 from 1.1, which gives us 1. We subtract 0.1 from 2.1, which gives us 2, etc. Now, with the class boundaries, remember they go 1 decimal place further than the data set. So since our data set goes to the tenths place, the class boundaries will go to the hundredths place. So instead of adding and subtracting 0.5 like we usually do with the whole number data set, we are actually going to add and subtract 0.05, again, going to the hundredths place, 1 decimal place further. So if we were to do that, we can calculate the first one and add the class width after that to make our lives a little bit easier, or you can go ahead and calculate by subtracting 0.05 and adding 0.05 to each one of them. Then we calculate the frequency. Remember, after sorting the list, this makes it pretty easy. Doesn't matter if you use the class limits or the class boundaries. Just count the number of values that fall within the given data set. Then we always want to double check and make sure when we add them up that it equals 25. Remember that there were a total of 25 envelopes. We have 5 by 5, which means there's 25 values. So you always want to make sure that you have all the values after you calculate your frequencies. Next, we have the relative frequency. Okay, remember that the relative frequency is equal to the frequency. Oh, I have this formula wrong. Hang on a second. Sorry about that. The relative frequency is equal to the frequency of the class divided by the sum of the frequencies, or basically how many numbers are in the data set. And we multiply it times 100%. So basically with the relative frequency, we're trying to figure out, what percentage of the values does each class represent. So for the first one, we have a frequency of the first class of 5, and we're going to divide it by the sum of the frequencies, which is 25, multiply it times 100%, which gives us 20%. And we do that for the rest of them. At the end, your relative frequency should be 100%. If not, consider going to a more specific decimal place. So now the next thing that we're going to take a look at, and this is new, is the midpoint. Basically, it's the average of the class limits for a particular class. So I can take the lower limit plus the upper limit and divide it by 2. And actually, I could do the same thing with the class boundaries. It doesn't matter if you use the class limits or the class boundaries. Your answer should come out to be the same. So I show you here that for the first class, I just used the limits, which was 0.1 plus 1, and I divided it by 2, which gave me 0.55. Now, you could do that for each one of the classes, but you might take a lot longer than if you just use the class width to help you figure out the rest of it. So remember, the class width is extremely helpful. Remember, our class width was 1, so I just added 1 to each one after that because the class width works, as long as you have a starting point. Let's take a look at the cumulative frequency. Now, cumulative means increasing or increased in quantity, degree, or force by successive additions. So if you think back to the example that I gave in class about the cumulative GPA, well, if you're currently a senior, well, you have a cumulative GPA of your freshman, sophomore, junior, and senior year. So it's kind of like everything before it is counted in it. And that's exactly what cumulative frequency is. It's how many values fall below the upper limit of that class. So how many values fall below 1 in this data set? Well, there's 5 that fall below 1. So my cumulative frequency for the first class is 5. Then for the second class, how many values fall below 2 in this data set? Well, 5 plus 3 is equal to 8. So it's basically like a running tally, and I can figure it out by adding up the frequencies up to that class itself. So for the first one, again, we had 5. For the second, it was 5 plus 3. For the third, it was 5 plus 3 plus 4. For the fourth class, it was 5 plus 3 plus 4 plus 5. And for the last class, it was 5 plus 3 plus 4 plus 5 plus 8. Now, because all of the values should fall below your maximum upper limit, your sum of your frequencies and your last value in the cumulative frequency should always be the same. That's a good check to have. Now, the cumulative relative frequency works the same way, but except instead of using the frequencies, we're going to actually use the percentages, the relative frequencies. So again, 20% of the values fall below 1. A total of 32% of the values fall below 2, and so on. Now we're going to take a look at histograms. Histograms use class boundaries on the x-axis. It's really important to know these key features because they differ for the next 3 data distributions that I'm going to show you. Another important thing to remember is these 3 data distributions or data displays that I'm about to show you, histograms, frequency polygons, and ogives, they are all graphs for quantitative data, meaning measurements, things that have to do with numbers. Nothing in terms of categorical data or qualitative. All right, so for a histogram, there's always 3 things that you need to list or label in any data display, and that's the title. Make sure you indicate the name of the graph that you're giving me, what does the y-axis, what type of frequency are you using? And lastly, the class boundaries. The x-axis is the one that is going to change for the most part, so keep in mind the class boundaries. Okay, so from here, I labeled my class boundaries of weights in grams. If you can give me the units, that's wonderful. And again, I gave myself my title with indicating the type of graph that we're doing, and we're using the frequencies. You also want to make a scale. That is really important, and make sure it's consistent. If you're going by 2's on the y-axis, you have to go by 2's the whole way through. With the class boundaries, with histogram, it doesn't matter where you start. Some people like to put the break. I'm not really picky about that. Other textbooks and stuff like to just make a line and there actually be a gap here. Whatever you're more comfortable with is fine by me. So then remember that the heights of the bars in a histogram represents the frequency of the class. So in the class where it's 0.05 to 1.05, there are 5 values in there. So I made sure to put the bar height up to 5. Remember that a histogram has no gaps. The only time that you would have a gap is if a frequency of a class was 0. Now, a relative histogram is pretty much the same thing. It uses the same class boundaries type of x-axis. The only difference here is, number 1, in the title, it says relative histogram instead of histogram. And on the y-axis, we label as relative frequency. That way, your audience knows that we're using percentages. So the heights of the bars represent the relative frequencies of the class. So in this first class, 20% of the values fell below the first, in between 0.1 and 1.0. And then 12% fell in the second class, and so on. We already calculated all of this information in that original crazy distribution in the beginning. Now, something to keep in mind, and this is true, I'm just going to show it for the histograms, but no matter which type of data display that we do, the regular graph and the relative graph will look exactly the same. It's just a vertical stretch or compression depending on the difference in the way the scales come out. So keep that in mind. Notice that the general shape of the top is the same. The shape is pretty much the same. Very important. So now we're going to take a look at frequency polygons. What is a polygon? Well, if you remember from geometry, it was made up of straight edges and it was a closed figure. So examples of figures that are not polygons is this cone-shaped figure. It's not a straight line, so it's not considered a polygon. And this one is not a closed shape. Now, there's more characteristics that go into a polygon, but I'm not really concerned about them. These are the 2 that you want to remember because this is going to help you remember all of the key features of a frequency polygon. One thing to keep in mind is that frequency polygons use the midpoints of weights. So I indicate that on the x-axis. It uses the frequency on the y-axis, and the heights of the points represent the relative frequency of the class. Okay? Oh, I'm sorry, represent the frequency of the class for this particular one. All right? So it's just the frequency of the class. All right? So now we take a look and I connect it with straight line segments. Do not try and make it a curve because remember, a polygon has straight edges. But be careful because here it doesn't look like the figure is closed. So we have a little bit of work to do. In order to get this to be closed, we actually have to create 2 faux midpoints. All right, so we need to create another one both before the lowest midpoint and after the highest midpoint. And that's just so that we can have a frequency of 0 and bring it back to the x-axis. Remember that a frequency polygon begins and ends at the x-axis. It is extremely important that you remember that. All right, and the relative frequency works exactly the same way. You notice here I have my 2 faux points, one before the lowest midpoint and one after the highest midpoint. And just to refresh your memory, the way that we would calculate this midpoint, these faux midpoints, if I wanted to go ahead to get to the next midpoint, I would add the class width, which in our case was 1. So if I want to go backwards, I'm going to subtract the class width. Generally, whenever I do the midpoints, I will always add these 2 midpoints in, just so that I remember, not inside the frequency distribution, but like above it and below it, just so that I remember that this is the type of graph, the one that uses the midpoints, I need to create 2 additional ones. That way it becomes a closed figure. It just helps you remember which characteristics go with each of them. The last graph that I'm going to show you actually has 2 names, and depending on the textbook or whatever that you're looking at, it may go by an ogive or a cumulative frequency graph. Either one is good to know. You need to know both of them in case they're referenced in text like that. Now, something very important, an ogive is very different. While it does use the class boundaries like a histogram, it's the only graph that uses the cumulative frequency. So remember, the cumulative frequency was kind of like how many values fall below the upper limit of the class. So that's really important. Another thing to remember is that it, just like the ogive, generally people will use segments. It makes it easier, line segments as opposed to a curve. It makes it easier to kind of estimate when we're reading off of a graph. And then the last thing is the heights of the points represent the cumulative frequency, but the frequency of the lower bound of the first class is always 0. And that's because 0 values will fall below 0.1, our lowest value. So that's why the frequency of that lower bound is 0. Every other cumulative frequency will fall at the top of, the upper limit of each of the classes. So taking a look, just so that we're clear, for the first class, we had a cumulative frequency of 5. Notice that that's the upper bound of that first class. And then for the second one, we had a frequency of 8, and that was at 2.05. That was the maximum, or the upper limit of that second class. That is something to really keep in mind here. Now, another thing that we take a look at, you want to make sure that an ogive is never decreasing. Cumulative means you're always adding on. So you should never have a line segment that has a negative slope. Okay, so that's really important. The other thing is it should always start at 0 and end at the number of points that you have in your data set. So we had a total of 25 envelopes. Notice that my last frequency was at 25. That's because all of the values have been accounted for here. So for a relative ogive, this is one of the most important graphs overall because this is the one that references percentiles. Remember I told you about the SAT scores, and generally they give you a percentile. And that tells you whether you are average, above average, or below average. This is very, very important. Cumulative relative frequency, another word for that would be the word percentile. What percent of people your age scored below you on the SAT 1? All right. Again, we start the same. The first relative frequency, a relative cumulative frequency, would be at 0% on the lower bound of the first class. And then we plot the percentile at each upper limit. All right. So just make sure in this case that you are clear, starts at 0, ends at 100%. In this case, because 100% of the values should fall below the maximum, and 0% of the values should fall below the minimum. And this is just kind of a quick reminder that it should always end at 100%, and it should never decrease, and that's for relative ogives. And that basically sums up the 3 types of data displays that we learned about for quantitative data. You should know the differences and the similarities between each of the graphs so that you can explain a relationship between them. Also, you should know how to construct a grouped frequency distribution for any type of data that I'm about to give you. So I hope that you found this video useful, and I hope that you do well on the next quiz.